Okay, welcome back everyone. In this video, we're going to be continuing our discussion of flux by talking about Gauss's law of electricity. We're going to continue with a couple more examples of how to calculate flux. So in this example, we want to draw a dipole and sketch three Gaussian surfaces, one which has positive flux, one with negative flux, and another with zero. So a dipole is just a positive and negative in proximity to each other. So a Gaussian surface for which we have positive electric flux is just one that encloses the positive charge. So positive electric flux would be that surface. Negative electric flux would be a surface like this. And a surface that has zero electric flux would be if you enclosed both. So remember that flux is just equal to the charge enclosed by our surface over epsilon naught. So the only thing that matters is how much charge is inside of our surface. So here's another example problem. Let's say we have a cone with base r and height h. It's located on a table and a field E goes through the cone. Determine the flux that enters the left-hand side of the cone. Well, it looks like this is going to be a really tough problem because all these vectors are going to be hitting the sides at different angles. As you go around the face of the cone, it looks like this. One will be coming in like that and like that and like that. Turns out we don't have to worry about that because as far as this field is concerned, the field just sees a triangular area and it's going into it. And this area has a height of h and a width of 2r. So therefore the electric flux is just going to be the field times the area. That's our definition of flux. And if we did a dot product, it would be very complicated, but it turns out we don't have to because we can just sum over the entire surface here. And so the flux is just simply going to be the value of the electric field times 2r times h, and it's a triangle, so times a half. So base times height times a half, and that just gives us EHR. So that's a fairly straightforward example. Here's another example. Say we have a vertical field, and it doesn't really matter if it's up or down, but we have the value of that field, and it's existing above Earth's surface when a thunderstorm is brewing. We want to find the flux through a car, which is rectangular size, top view of 5 by 3 meters, if it's traveling on a road with a 10-degree slope. So the car approximates like a line, if you look at it from the side, that is. And so we have an area that goes kind of like this, and we have 10 degrees. So the area between, the angle between the electric field and the area vector is, well, you could say it either way. It's either 10 or 170 degrees, but the flux is just going to be EA cosine theta, which will just be E, and then A is 15 square meters, and then the cosine of 10 degrees. So we won't put in the numbers, but that's just how you set that one up. Okay, and we'll do one more example. So now let's say that we have a uniform field of AI plus BJ. So if I draw my coordinate system, this is a right-hand coordinate system. So AI plus BJ means that this field is actually going to be kind of going at an angle. It's kind of hard to show that, but that's kind of in the XY plane, if you will. And it's going to come this way and amount A, and it's going to go over this way and amount B, and then we can calculate the flux through the area for all these different planes. So first of all, for the XY plane, well, that's the plane which is denoted by I hat and J hat, and you'll notice that there's no component of the field in the k hat direction. So one way that we could write this is that the area vector is equal to a k hat. And that orange is not really showing up, so we'll switch back to red. Maybe we'll do a purple. Okay, so a is equal to a k hat, and the field v is a I hat plus b j hat. And you'll notice right away that a dot v is 0 because there's no corresponding I or j in the area and there's no k in the field. Okay, so for the xy plane it's simply 0, and if you look at the diagram, there's no field lines going through the xy plane. They are going sort of parallel to the plane. Okay, now the xz plane, that's the one which is sort of right here, denoted by I hat and k hat. So in this case, we could just say that a is equal to a j hat. So that means that the flux, which is a dot v, we'll use the same value of v up here, is just going to be ab. And that's it. That's all we need to do is just take the dot product of a and b, or a and v rather. So in the xz plane is just the value of ab. And then finally, so that's part B, that's part A. Part C, the YZ plane, so that's this guy right here, denoted by j hat and k hat. And we just do the same thing, and in this case, the normal vector is going to be a I hat, because it'll be kind of going this way. That'll be the normal vector, just like before it was going in the j hat direction. Hopefully you can tell from my 3D drawing here. So the flux is going to be, again, a dot v, and in this case it's going to be a, big A, little a. Okay, so we have 0, we have AB, and we have AA. That was nice. We didn't have to do any integrals, and that's because it was a constant value uniform field. Okay, so now that brings us to Gauss's law of electricity. And we saw this in the last segment when we looked at the flux for a point charge. And we noticed that if we had a point charge, here's all the field lines coming out. And if we surrounded it, we could calculate that the flux was equal to the surface integral of E dot dA. And when we did this for a point charge, what we found was that the electric field was that of a point charge. Remember that the point charge is 1 over 4 pi epsilon naught r squared times q. And then we had the integral of dA, which turned into 4 pi r squared. So notice that everything is canceling here. The 4 pi and the r squareds are canceling to give us that the flux is equal to q over epsilon naught. Now we rearrange that and we get Gauss's law, which states that if you want to find the charge enclosed by a given Gaussian surface, which is the sum of all positive and negative charges, you take epsilon naught, which is a constant. It's how easy it is for electric fields to permeate space, and you multiply that by the flux. And hopefully it's not too cut off, but the flux is right down there. And that tells us that Q enclosed is epsilon naught times the flux. So this is a very simple form, but it's very powerful because it tells us the relationship between charge and flux. So let's look at this in a couple of different formats. Okay, this was the first one that we saw, Q equals epsilon naught times the flux. Now you can also replace the flux with the actual expression for it, which is the surface integral of E dot dA, and that can be helpful. But the way that I prefer to write Gauss's law is as follows, that the surface integral of E dot dA is equal to Q over epsilon naught. So on one side you have the flux, and on the other side you have information about the charge that's enclosed. So this one in the box, this is really my favorite version of Gauss's law, and you can use any one that you want, but I'm going to be solving problems using this, and this is the enclosed charge. Now the last thing I should point out is that this is a differential form. Okay, or sorry, this is rather an integral form of Gauss's law. Integral because of this surface integral here. Okay, so that's these first three are really all the integral forms. But you'll find out, if you haven't already, in multivariable calculus, that you can also write a differential form. And we won't get too much into this just yet. We'll save this for when we do electric potential later. But there's a operation called the gradient. And if we take the basically the gradient of the electric field, del dot E, we get information about the charge density. And we talked about rho a little bit earlier, but it's basically charge over volume. And typically we write it as dq dv because it's not always a constant value for the charge density. Now, one other thing that we should mention is that this del thing is the partial derivative with respect to x, I hat, plus the partial derivative with respect to y, j hat, plus the partial derivative with respect to z, k hat. So if you apply that to the electric field, where the electric field is equal to Ex I hat plus Ey j hat plus Ez k hat, well then that just turns into partial Ex partial x plus partial Ey partial y plus partial Ez partial z. So that is kind of like the gradient, if you will, for the electric field. And so this is something that we'll be using a bit later on in order to calculate electric potential, but we're not going to look at it just this moment. So let's look at a few more things concerning Gauss's law. The most important thing is what we call the Gaussian surface. It is any closed shape in space. But we should point out that not all Gaussian surfaces are created equal. They all give the same answer in Gauss's law because the integral of E dot dA doesn't matter on the surface for that surface integral, okay? Because that's always equal to Q over epsilon naught, Q enclosed. However, the whole point of using Gauss's law in the first place is to make the math a lot easier. So, for example, you would not want to have a point charge and surround that by a Gaussian cube. And the reason for this is if you think about what this point charge is doing, let's say it's a positive charge, it would have an electric field that is going outwards radially, so like so and like this and like that. And so the point is that at every single point on the surface of this cube, if we wanted to think about this surface integral, E would be going out radially, but dA, for example, would be going out in, perhaps it would be going in the I hat direction, it would be going in the k hat, or even in the j hat direction. And that would be true everywhere on the surface of that cube. So if you just looked at one surface, the field would be going all sorts of different directions, but n would be going straight up. So you would have to perform a very complicated surface integral where you break it up into pieces, and at every point you would have to do EA cosine theta. And this is actually a job for computers with numerical integration. So we don't want to use a cube as a Gaussian surface. We always want to pick Gaussian surfaces that make sense. So what can we use Gauss's law for? We can figure out how much charge is enclosed by a surface. Sorry, go back. Okay, so we can use it to find Q enclosed. But more commonly, we use it to find the electric field at a point in space. So E of r. Okay, now let's do one quick example. Okay? And then we'll move on. So this is going to be a point charge located at distance d from an infinite plane, and we want to determine the electric flux through the plane due to the point charge. So this is an infinite plane. I'm not going to draw it like this, but we have a point charge right here. Okay? And we just want to find the electric flux through the plane due to this point charge. Okay, now as I just said in the last slide, this could get really complicated if we had to use the infinite plane as our Gaussian surface. But instead, let's just take an infinite sphere to enclose that. And it turns out that it's a very easy problem to solve. The electric flux is simply Q over epsilon naught. And it doesn't really matter what the geometry is in this situation. Okay, so we're going to stop here. In the next video, we're going to see how geometry benefits us and makes our calculations easier.